Morning, everybody.
Morning, Prof. How are you?
Who is speaking? Hi, Philip. Okay, so this is a fairly shortcut, but it's not easy to find out where to do this whole sensitivity analysis. In the user manual, I'll just put that on the screen quickly. You can look up sensitivity analysis, and then this thing, tool sensitivity analysis, is actually wrong. So if we go under tools, there is no sensitivity analysis here at all. So it's under optimization. You've got those two options. Now, why am I placing emphasis on the sensitivity analysis as one of the important tools in DWSim? In CPS 420, we're going to be doing optimization. We'll be doing just a week-long course in optimization, and you'll need to do an assignment where you use DWSim to optimize a spreadsheet. Now, optimization is, you'll see it has its uses, but then you've got to have real physical constraints to make it valid, because it's very often that that the best result is where something is physically impossible. For instance, the highest possible temperature will give you the best results on your simulation, but the highest possible temperature is not going to be okay for materials of construction. And in this case, we're going to find that the temperature of the Gibbs reactor must be as low as possible. But there will also be a constraint on how low you can go, because as the temperature gets less, the rate of reaction gets less, and therefore you're not operating at equilibrium. And remember, we've got a Gibbs reactor, therefore it means we're operating at equilibrium. So a sensitivity analysis is a really useful tool. It is because what we've got here in TUT4 is a workable solution to making methanol from CO plus water. And that is not what design is about. What design is about is, yes, the process synthesis, as in putting an absorber in. Sorry, I've realized too late that the absorber is probably was added as TUT5, not as TUT4. But at least I don't have the recycle, which made the process a little bit less stable. So what we want to find out, what temperature. We chose a temperature so that we got 600 kilograms per hour coming out here, and then changed that because I put in the absorber. I see it's now 475 kilograms an hour, but never mind. We're going to try and optimize how much product we're making, which is the methanol. And the methanol in this flow sheet comes out at the top of the distillation column. And we're going to just see what temperature we should design to, so that we can get the most methanol. And there we're going to just use the thermodynamics at temperatures high enough where we know it's going to be at equilibrium. So so let's go and start the sensitivity analysis. Before I start, hands up anybody who has tried this, whether you've succeeded or failed. Have you tried this sensitivity analysis? Eliska?
Not yet.
You haven't done the Philip. Okay. It's yeah, it's to me fairly unintuitive. So let's go through it. Sensitivity analysis. Right, now, one thing I don't like about the way DWSim does this, I wish they do this in a separate window so we can still see the flow sheet. Because now let's go with a new case manager, a new sensitivity analysis. The name, we can rename it as water gas shift reactor temperature. And right, here we've got independent variables, dependent variables. So independent variables is the ones you're going to change that you yourself has control over. Dependent variables, this must be the methanol flow rate at the end of the flow sheet. So the independent variables, we're going to change the temperature of the Gibbs reactor, our Gibbs 01, and the property of that is the outlet temperature. And the lower limit, I did try 500 and it didn't work, so I am going with 700. And we want to end on 1,000. That's 4 points we like to evaluate. And degree C, and the current value is 856 degrees C, which is correct. And now note that you can put a second independent variable in, which is rather nice. So you can do it in 2 dimensions, and that would be rather useful. But just for the purposes of this thing, we're going to do the single dependent variable, the single independent variable. Dependent variables. Now we can look at whatever we want to look at, how it changes on the flow sheet. I'm going to just add one, and that is, I suppose we can write in a name, methanol product. And the object is going to be the stream coming out, which is MSTR08. Now, if this had been in a separate window, it would have been easy to go and check which stream it was that we're looking at, but I do remember it was MSTR08. And the property is, now there'll be lots of properties of a stream. And I'm looking for M for mass flow rate. And there it is, mass flow. Now, at first I tried mass flow liquid 1 methanol. And mass flow mixture methanol. But because this stream normally on the top of the distillation column, you would expect to have a liquid product stream. In this case, it was a vapor product stream. So anyway, let's choose mass flow because I know that's going to work better. And now, you see, now it gets, oh, therefore, now we go to results. So we've been going along these tabs from left to right, and now we go to results, and we can start the sensitivity analysis. Oh dear. System closed, search forums, unhandled error. No, why did it work yesterday and not now? It didn't calculate on 700. Let's go back to the original. Now, how to get back to the original thing? There was a drop-down list somewhere where I can choose. Oh wait, it's this one, flow sheet. Yeah, so these things on the top we can go back to the sensitivity analysis just by using these things at the top. And that is also the way that you could look for flow sheet. You could look for what is MSTR08, which is the if you wanted to find out which stream is the one that has the methanol in it. And this one you can see has got 98% methanol overall, and it is 475 kilograms per hour. So that is correct. What I want to do here is to change this temperature to 700 and see if the thing will still solve. And that's where the problem is. I don't think so. I don't think we needed to put it under variables. Let's just go back to sensitivity analysis. Dependent variables. MSTR is a dependent variable because we're going to change the temperature and then we want to see what effect, and this is a dependent variable, the mass flow of MSTR08. So I think we did it right in that respect, but I'm worried about 700. So I'll go back to the flow sheet. Oh, that's semi-solved. So it had a problem when it got here. So let's go for 700 degrees C. We change over here, 800 degrees C. Still doesn't solve. I'm pretty sure I used the right. I used the same file as yesterday. .4 gives distillation. All right, let's go to 900. I know that 500 was a problem yesterday. Okay. Let's have a look at this temperature here. 40 degrees. Okay, I'm going to delete the absorber. And hit F5 solve flow sheet. All right, so that's more stable. Let's go down to 500. All right, that works. Now let's have a look what we've got here. And stream 8 is still 98.4% and 146. So we're losing a lot of methanol somewhere. Only 146 kilograms per hour. Have a look at this one. No, we can't. 700 kilograms per hour. Have a look at this one. Oh, 2,000. We're losing virtually everything out the top here. Because there's so much gas compared to the amount of liquid that we lose a lot of our components out that way. So I'm just going to make this an unrealistic 0 degrees C. Enter. And that seems to be happy. And now let's have a look how much we're losing here. It's still about the same. This one, 700. This one, 146. It's the same. Don't really understand that. I did say enter. Never mind. Let's go on with the sensitivity analysis. So we're still able to, with the sensitivity analysis, change this temperature and see what we're getting out over there. So let's go back to the sensitivity analysis and methanol. Yep, that's the dependent. Independent is still, well, we can go right down to 500 now because it's more stable flow sheet. And dependent variables, and now we go to results and we run it again. Start sensitivity analysis. There we go, at least it's giving numbers now. Oh, nope, still fails. Okay. Restoring simulation to its original state. Okay, good. Flow sheet. Right, so the flow sheet is still working. What I want to try is seeing what happens if we go to 1000 degrees C manually. It does solve. So what's its problem? We got it. Yes, look at.
Sorry, Prof, can you hear me?
Yes, I can.
Prof, under the variables tab, the dependent variable tab.
Yeah, let's go there. Sensitivity analysis. We must get out of. Oh yes, dependent variables. There it is. Yes.
I think you need to add it on this left column that says variables, because right now we're adding it under expression.
Parameters. Thank you. I'm going to remove this one.
That should work, Prof.
Yeah, of course. No, you're absolutely right. So we are talking dependent, which is MCR08, and we're looking for mass flow here. And right, I misunderstood when you texted mass flow there. And we should be okay. Results. Start it again. You see, now we've got a result there. Oh, look at that. Big difference. And there's a maximum. Oh, isn't that cool? Wait a minute. I'm going to go back and make the increment much less. So we go back to independent variables. We're starting at 500, going up to 1000, but we're going to go up. That's 6. We needed 6, but we'll make it. Is it 12? 13. 13 units because it's the fence post. Okay. That's dependent variables results. Start sensitivity analysis. No, I didn't get an equal number. I should have made it 12. Or 11, I think. 11 would have been right. That's cool. That's so nice to get a maximum. Okay, so now we've got results. We now go to spreadsheet. I thought it got populated immediately. Okay, let's go back to the sensitivity analysis. There must be a thing where we can send data to the new worksheet. That's right. Okay. So there's a new worksheet and it's been filled with the data. And now we find charts and add a new. No, let me just go back to the spreadsheet and see if there's an add a new chart somewhere here. No, let's go back to charts. Add a new 2D. What bothers me is it is selected, the data is selected. There we go. Right click on the data, create a 2D XY chart from the selection. There we go. Oh, that's a fairly sharp optimum. Quite surprising. Huh. All right, so that's the maximum we can get at 670 degrees C odd, 680, and this is now where you start to be doing real design. It may not be the best temperature to use, because we're not taking into account, the cost of the equipment and the cost of materials and the cost of how much energy we'll need to run at this temperature. But it gives a good feel for what's going on with this particular flow sheet. Yes, Philip?
Prof, when we still had the absorber in, we got 560 kilograms per hour of out of methanol. Would that not be better than?
Yes, of course. We are losing so much. Let's just go back to the flow sheet. We're losing so much out of vapor stream 9. I'm going to click on it and then go to results, compounds, and mass flows. And let's have a look how much mass flows. Small flows. Mass flows. There we're losing 183 methanol, and the absorber would have recovered most of that, because this is where we put in the absorber, and we recovered most of the methanol that would have gotten lost over here.
So now, when we do a design, would we then rather add in the absorber and use a higher temperature and use the maximum on that in the sensitivity analysis?
And if your absorber actually is working at all of those temperatures, that's fine. But as the temperatures change, the stream changes, and therefore the conditions that you must operate this absorber at vary. So it's what you would want to do is to optimize. In other words, change the conditions of the absorber as the conditions of VSTR 09 change. As you get different compositions coming out of vapor stream 9, you want to have the more correct operation of this absorber, and that would now be heading towards optimization, because you're varying multiple variables in order to get the best out of here. Now, what we've got with our sensitivity analysis, it's this chart. What we've got, it looks like an optimum, but it's not necessarily, because as you say, if you've got the absorber in, you might find that the optimum lies somewhere else. But that would only be valid if you were optimizing the absorber at every temperature, at all of these conditions. And that's what an optimization program will do.
Can we do that by adding the absorber as a second independent variable or not in the sensitivity analysis?
Yes, you could, but it's gonna. The trouble is with the sensitivity analysis is that it crashes if you've got the wrong values. So, like with me, it crashed it crashed even on the base case for some strange reason, I don't know. So I just took it out so that the flow chart, the simulation would be more stable. I took out the absorber. Now, if we go, let's go back to the sensitivity analysis and independent variables. So if we added a second independent variable, it would probably be, it'll be that absorption column, and the property will be how much, no, it won't be the absorption column, it'll be the water that goes into that absorption column. Because as that that vapor stream changes in composition, you'll have to add more or less water. I guess what you could do is to simply use much more water than you actually need. I'm gonna start over by closing this simulation. And opening .4 again. And now having a look at the stream. I've got 3,600 kilograms per hour. And I want to change that to 5,000. So when we do that, we're going to be putting a lot more water into this simple, what do you call it, to this distillation column. But it shouldn't affect what we're getting out over here. Yeah, it's still 451. It was 475. So we're getting a little bit less out because we're losing more down here. This one, you can see there is methanol in there, 0.01. It's about 1% methanol, but the flow rate is very high. You won't be able to read that, but the flow rate, mass flow, 6,000 kilograms per hour. 1% of that is methanol, and that's methanol that gets lost. Okay, so now let's do the sensitivity analysis again, because hopefully it's going to be more stable. But first, I'm going to try 500 degrees here. Or let's be conservative and try 800 and see if the thing solves. Oh, I see. The absorber is not solving because MSTR 12 is not there. Now, I thought with a very large flow rate here, we'd be able to get it to solve anyway. 25 degrees C, we can't really go lower.
Just try and solve the whole flow sheet there at the top. It worked for me just now.
Ah, okay. Let's go to the base case of 500 and see if we can solve it there. And now, this won't work on the, if we have to say solve again every time. Then I'm worried that it won't work on the sensitivity analysis. But you managed to get it to work. Let's try.
Yes, but I don't get an optimum. So the lower limit is
the lower temperature
is the highest, but it's not the optimum. It's not the max.
No, that's fine. 299 compared to 475. That's pretty poor. What did you get? No. Let me quickly do a sensitivity analysis. So this is RTO1, property, outlet temperature. Why is it already changing stuff on my flow sheet? Huh. Okay, let's just carry on. Sensitivity analysis, lower limit 500, 1,000. that'll be 6. And dependent variables, add them over here, not on the other side. MSTR08, mass flow. And results. Results. That's that funny thing coming out. Okay, no, mine's not running.
Try 665 degrees Celsius as your lower limit.
Let's just run it, and let's go back to the flow sheet.
Rob, I did exactly the same as you now, and mine ran.
It was ran. Okay, I'm just remembering that I changed this one to 5,000 kilograms per hour. So.
Oh, I couldn't remember what you changed it to, so I changed mine to 8,000, and then it works.
Great, that's very high. $8,000. There we go. Enter. Now work. Yes, it worked. All right, let's go back to the sensitivity analysis and see if we can get that to run. Okay, let's go back to the temperature. Flow sheet. Let's go to that Gibbs reactor and we go to 700. Enter. Now you see when I have to manually solve it, it's not right. Yeah, I've got something different to yours, Philip. Somewhere on this flow sheet that's making it not work. So the sensitivity analysis, I'm going back to independent. I'm going to start at 700, but I don't think we're going to get much luck here. And that'll be 4. Results start. Yeah. Okay, well, yeah, you need to get a stable simulation before you can do this thing successfully. But at least we did get one of them to run successfully, and it was very successful in that we managed to get an optimum, which is always a surprise, or a maximum flow rate. It's not an optimum, because an optimum refers to all of the variables being changed to give the maximum and the maximum flow rate, and that would be an optimum. But it's still a very useful tool when you get that to run, and you can get the sensitivity of the Gibbs temperature to the how much of the product you can get out. And that is real design. That is where you start making a much better flow sheet than simply having something that works. Okay, guys, any questions then? Righto. I guess we can call it a day, and I'll see you on Monday. Yeah.
Thank you, Prof. Enjoy the weekend.
Cheers, everybody.